quadratic equations, solving them again and more. Going to keep looking at them, you guys. Okay, the area of a rectangle can be expressed by this equation if the dimension of the rectangle are known to be linear factors. In other words, x plus 3, x minus 5, all those types of things. Of the expression, write each dimension of this rectangle is a binomial. Write the area in terms of the product of two binomials. So we know that a rectangle has a length and a width. We know that area is equal to length times width. We're given this information, x squared plus 2x minus 3. We're told that that's going to be a product of two binomials. Well, that implies factoring, right? Negative 3 and 2 can only be 3 and 1, where one of these is negative. That's got to be positive, that's got to be negative. So x plus 3, x minus 1 is our linear factors. If we plug that in here, area is equal to x plus 3 is the longer side, x minus 1 is the shorter side. And we've actually labeled the diagram already. All right, with that in mind, let's keep going. C, remember we have area. It's 21 units squared. Find the dimensions of the rectangle. So 21 equals x plus 3, x minus 1, correct? All right. However, we can't solve this when it's set equal to 21, so it'd be better if we were in this form. X squared plus 2x minus 3, where we subtract 21, and we get 0 is equal to x squared plus 2x minus 24. Now we're looking at factors of negative 24 that add up to 2. Well, 24, 4, and 6 are two reasonable numbers, where the larger one has to be positive, smaller one then is negative. So 0 is equal to x minus 4, x plus 6. In this case, we know then that x is equal to 4 and negative 6. Our problem here is that a length can't be negative 6, but we can look at that. Maybe that's not actually our length. Remember, the dimensions of the garden showed up as area equals x plus 3, x minus 1. If I were to plug in 4, I would get 7 times 3. Well, interestingly enough, that equals 21. What if I plugged in negative 6? Right? I would get negative 3 and negative 7. And that can't be. So that's why we eliminated the negative 6. It's not going to give us a reasonable solution. So we now know that our actual dimensions of the garden were 7 by 3. Okay, so for this next problem, I'm going to suggest you pause this and give it a try yourself. See if you had made sense of problem number 1. So go ahead and pause it. I'm going to go ahead and work it and then show you the results as we go. Okay, so hopefully you're coming up with these answers. If not, pause the video and see if you can get it figured out. We know that x can't be negative 2. So therefore, when I plug this back in to my area formula, where 7 is equal to 6 minus 5 times 6 plus 1, That's a 5, trust me. We end up with 7 is equal to 1 times 7, which is our dimensions. Lord Byron is designing a set of square garden plots so some peasant families in his kingdoms can grow vegetables. The minimum size of the plot recommended for vegetables is at least 2 meters on each side. Remember, this was a square garden. Lord Byron has enough space around the castle to make bigger plots. He decides that each side should be a minimum of 2 meters plus an additional X meters. What expression can represent the area of one individual garden based on the undecided length, additional length X? Well, area is equal to X plus 2 or 2 plus X, and that's squared, whatever that's going to be. There are 12 families in the kingdom who are interested in growing vegetables in the garden. What equation can represent the total area of the 12 gardens? Assume all the gardens have the same size. Well, if that's the case, then our area is going to equal 12 times the X plus 2 times the X plus 2, right? For our total area of garden needed. Part B, we just got finished saying area equals 12 times X plus 2 squared. If the total area available for the gardens is 300 square meters, what are the dimensions of each garden? So they're now saying 300 equals 12 X plus 2 quantity squared. And now what? Now we've got our work cut out for us. And I'm going to suggest at this point that we solve this by taking a square root. So we're going to divide by 12, divide by 12, and we're going to get on the right side X plus 2 squared. On the left side should be 25. We take the square root of both sides and we get plus or minus 5, don't forget the plus or minus, equals X plus 2. Come up here, we're going to subtract 2 from both sides, and we're going to get X is equal to plus or minus 5 minus 2, or X is equal to 5 minus 2, which is 3, or negative 5 minus 2 is negative 7. All right, so is it reasonable then for X to be a negative 7? Take that negative 7, plug that back in. No, it's not reasonable, because then we'll have a negative radical, so our negative area, and we don't want that. So we're going to eliminate that. Could you have multiplied that out and solved and got the same thing? The answer is yes. I wouldn't, though. In this case, when it's set in vertex form, go ahead and solve by taking the square root. Part D says find both values for X that make the equation in part C true. The solution set. Okay. What value of X does Lord Byron need to add to 2 meters? Well, he needs to add plus 3. So we're going to end up with a 5 by 5 garden. Okay, so here are some practice problems that you should take a few minutes and solve, and I'll give you the answers. Okay, so here are the answers that we're looking at. Notice that sometimes you end up with a square root or a radical as an answer. That's okay, depending on the problem. This is not a application problem, so you have to worry about plus or minus. Um, Number 5 was pretty straightforward. Number 6, we ended up with fractions. Okay, I know we love fractions. Get to know them. You could have left that as an improper fraction if you wanted. And then number 7, 3 plus or minus root 3. And we want to put this in a complex form where the whole number's on the left plus or minus the radical. So there's an order to that. Okay, our last problem, last example. Peter's a painter and he wonders if he would have time to catch a paint bucket dropped from his ladder before it hits the ground. He drops a bucket from the top of his 9-foot ladder, 9-foot ladder. The height h of the bucket during its fall can be represented by this equation. That's pretty cool. They gave us the equation where the height is measured in feet from the ground and the time since the bucket was dropped, t, is measured in seconds. After how many seconds does the bucket hit the ground? Do you think he could catch the bucket before it hits the ground? Be sure to justify your answer. Now, let's go back and look and make sure we make sense of this. That tells us that this is 9 feet above the ground. This is velocity, so we know this is a parabola that's facing down. And I would start by factoring out. Go ahead. We want to we want it to hit the ground, which is 0, right? So we're going to set this equal to 0, and I'm going to factor out a negative at least. So negative 16t squared minus 9 gives me that difference of squares equals negative 4t minus 3 times 4t plus 3. And because this is set equal to 0, we now know that either 4t minus 3 is equal to 0 or 4t plus 3 is equal to 0. 4t equals 3, or t equals 3/4 second, or 4t equals negative 3, or t equals negative 3/4 second. Again, we're going back to what's reasonable. You're not going backwards in time. So 3/4 of a second is our answer. And now the question was, do you think he has time to catch the bucket? Now, is Peter at the top of the ladder? Where is he standing? If he's standing next to the ladder, maybe. If he's on the ladder and has to get down, that's a whole nother question. I'm going to let you justify that. Good luck with continuing to factor.